Hi, it's Mike Barnes here once again to talk to you about solar PV. You know, before you can get a good handle on how solar PV really works out for us, you really have to understand how electricity gets generated. And what I've done is I've put a short, less than 10-minute video online for you to look at. You can access that either on YouTube or Vimeo, or your D2L online course should have this video embedded. So my suggestion is you would pause this video now and go to alternating current. It's actually called AC Electricity Generation Explained. And then come back and we'll move on from there. This next slide speaks specifically about understanding the electric grid. You know, today's electricity grid is centralized. What that means is you've got big, large coal-producing plants, gas-fired plants, hydro plants that produce energy for thousands and thousands of folks. That energy gets transmitted many, many miles from transmission lines at upwards of 100,000 volts to 1,200,000 volts, also referred to as 100 kV or 200 kV, as you can see here in our slide. But in order for centralized electricity to get distributed, there are really two effects that happen with this. First off, there are significant cost reductions because these are massive plants, and so they have some tremendous economy of scale on the one hand. On the other hand, because you're transmitting this electricity over long distances, you've got voltage drop of 7% or even more, depending on the amount of distance that those electrons have to move, and through Ohm's law lose some of their actual power producing potential. Now, the transmission lines that are very, very high voltage, those electrons are extremely excited. So excited, in fact, that you can stick a fluorescent tube in the ground and it'll light up. Those transmission lines that are high voltage transmit that power to central substations that are 32 kV to 115 kV. This K here, of course, represents thousands, so 32,000 volts to 115,000 volts to distribution substations. From those substations, transformers again step down that voltage to 3.3 kV, upwards to 25 kV for distribution and also for local delivery. Finally, at 1 kV and below, we're using that 1,000 volt target for industrial and commercial facilities, and I put this bullet point in because really we're 600 volts or so to stay within National Electric Code. That's this next bullet point here, less than 600 volts, and we comply with the National Electric Code, which does cover some stuff up to 1 kV as well. Less than 600 volts is used in most commercial and residential applications. So there's an overview of the electric grid in the U.S. The next thing to really understand is your electric bill. At this point in a brick and mortar class, I would have students bring in their utility bills, their electricity bills, and we would actually break them down. They're arranged very similar to the way that the grid in the previous slide is arranged, where there is a generation charge. This generation charge is often referred to as the price to compare here. There's a transmission charge, there is a local delivery charge, and then there are taxes and other surcharges included that may be included in your bill. Take a look if you have one of your invoices around, and you'll see that your bill is broken up in this way. There are also, I have noted here, SREC, which stands for Solar Renewable Energy Credit, and educational charges that are a component of your electricity invoice. And then many of you will have times of peak demand of that electricity, which will cost more. Each utility is a little bit different with this, but when we are all demanding a lot of electricity, it actually costs us more money. And I would also point to another video here, times of peak demand cost more. See the video about how demand for electricity drives demand for solar PV. That is also on Vimeo, as well as YouTube, as well as your D2L learning source. This next slide talks then about distributed generation. You know, 2 slides ago, we're talking about centralized electricity distribution. Now I want to take you to this next slide of distributed generation. What exactly is that? Well, distributed generation is when power is really produced closest to where it can be used. So technologies like solar PV and thermal are used for this, as well as wind, microhydro, fuel cells. I've got them all listed here. Generators, combined heat and power, and other forms of natural gas technologies, which we'll discuss a little later in the course. The next slide talks about why solar's been around since the 1950s, but why did it take so long to catch on? Well, first off, solar, when it was first discovered, was very expensive, costing $1,000 per watt or more in 1960. Today, the cost is less than $3 per watt if you've got it installed on large-scale installations. That is more than 1 megawatt projects. The price today is down in the $2, mid $2 range or so, all in. That is with permits, inspections, and all the stuff you have to do to put in those large-scale PV arrays. Again, that's quite a drop from the 1960s. And actually, solar did catch on, that is at smaller scales, through photodiodes and light sensing technologies. The next slide speaks about space and small scale, the off-grid remote solar PV applications. Of course, you're not seeing the stuff in space except in pictures, but some of the small off-grid stuff you do see, especially remote monitoring and that sort of stuff. But to speak to this, satellites are using PV modules. They're highly efficient, they're low weight, but they're expensive. I often get asked, why aren't solar panels more efficient? Well, the ones in outer space really are efficient. They're in the 30, 40, some of them even approaching the 50% range in efficiency, but they are using compounds that on Earth would be poisonous. Arsenic is one of them that I can think of. The Earth program, you're going for bang for the buck, but the extraterrestrial stuff, you're really not sparing the same kind of expense to get done what you need. Off-grid systems then, think about your hunting cabin someplace, or if you were using power where you were not connected to a grid, say in Africa or a place where the grid goes down all the time. Off-grid applications really need backup to operate 24/7. Of course, the sun's not shining at night, so you need some sort of either battery storage or generators or other renewable technologies to match up to solar to make sure that you've got power 24/7. Finally, on this slide, PV solar is used pretty much everywhere for, and you've seen these all over the place, signs and street lighting, small electronics charging. I mentioned again, I'll just point out that we've got a program going over in Africa where we are distributing solar for cell phone charging, which is a big deal there. There's also PV solar used for emergency power and monitoring for stuff like remote gas well heads in the middle of nowhere where you have a small battery that gets charged during the day, and then you've got the monitoring equipment that doesn't use a whole lot of electricity, that may be speaking via even satellite transmissions to let folks know if that wellhead may be leaking gas. That would be a bad thing, of course, but folks can't just stand around and watch that. So that's some of the monitoring that happens. And also, solar PV is used for water pumping. If you think about cattle that may be in the western high desert regions that require round-the-clock water supply, and sometimes water's available, sometimes it's not, like in the middle of winter where everything's frozen, but yet you're pumping groundwater out that is going to be warm enough to be able to water the cattle, and so the sun comes up and the pumping operation starts, fills up the water. It may even freeze overnight, but then the next day more water is pumped in and the cattle are able to drink. Often I have students ask me at the beginning of a class, well, how might I work in solar PV? And I've got a couple of slides that outline the various areas that are available to work in the PV market. It's pretty vast. First, there's in the laboratory, such as the National Renewable Energy Lab in Boulder, Colorado. There are manufacturing plants all around the world, many in China. You may have heard in the news how China has been very competitive with their solar panels. Some think it's because they've kept their yuan artificially low, which means that they've got some very cheap imports into the U.S. Anyway, you slice it, manufacturing plants are producing PV solar just about everywhere in the world. There are also companies that are building robots that actually make the modules, as well as the other component parts, inverters and racking. We have sales and marketing, which is its own component of the solar PV market share, if you will. In fact, that's probably where the largest amount of growth is in this marketplace right now, because folks are still not 100% educated on what the technology is, and so sales and marketing leads the way in educating consumers as well as future employees into the market. There are engineering positions in this market, in the PV market. The first one I have listed here is, of course, for electrical, for the systems design, as well as then number 2, the mechanical and structural components. For every project that my company builds, I need solar. We need to have a mechanical structural person verify that the roof or the ground mounting systems are good, particularly that roofs will actually hold the weight of adding solar to them. And then finally, the civil engineering side of this, particularly for large commercial ground mount PV solar systems, to calculate particularly runoff from rain, retention ponds that may need to be built, because solar modules, they are impervious surfaces, and so rain runs off of them. How do we get rid of that rainwater if we put in a big solar farm? As well as even glare studies for arrays that are close to airports. It's not immediately intuitive that solar panels are designed to capture as much of the sun's power as possible, but many airports require a glare study be performed in and around the airport to make sure that planes flying in and flying out aren't blinded from glare from the face of the glass on these modules. The next slide, how might I work in solar PV 2? There are purchasing folks required. PV is really a worldwide market, and folks purchasing in this sector have to be able to, in many cases, negotiate with folks who may be in China or Canada or the Netherlands or Spain, because it's not like running down to your local hardware store to buy parts for solar PV systems. Many of the large arrays are coming in containers aboard ship, and many of the modules are bought in container loads from other countries. So this is truly an international type of purchasing that gets required in the PV market. There are also pre-assembly teams. In other words, when materials come in for a PV array, someone's got to put those systems together. you've got a choice of either putting them together on the job site, building them right on the roof, but in many cases that's not necessarily the fastest, most efficient way to do it. If you're able to put systems together in a controlled environment like a warehouse where you've got good lighting, good heating and cooling, and you're able to put multiple modules, PV modules together, and then lift them onto a roof with a crane, you can get projects done a lot faster. So project pre-assembly teams are required. Operations managers coordinate projects that are in the field, so there's plenty of openings for good operations management folks. Project managers would be another one that would go under that heading. And then, of course, installers. A lot of folks taking the solar PV course think, well, I'm going to come in here and just be an installer. But you can see, hopefully, just from the 2 slides we've looked at so far, that there are many, many other areas to enter this field. Installers, I have noted here, should have electrical and mechanical backgrounds to install effectively. Next, I have inspectors and standards enforcement. These would be your code officials, as well as the folks that set up UL requirements and inspection agencies depending on the area in which you're working. Most of the U.S., because of the commercial and residential building codes, have adopted specific requirements based on their county or township or area, and so each one is different. You can enter this field and be an inspector of these systems. There's a vast amount of administration needed for these systems I have noted here, to track the warranties, to sell. Again, there's that acronym again, SREC, to sell the solar renewable energy credits back to utility companies, to also help customers recover incentives, because this industry is highly incentivized at this point. And we find that you've got to know what those incentives are for each area, and be able to help the consumer get those incentives back after the systems, oftentimes after the systems are built. Actually, it happens before then too, in just making reservations for rebates and so on, even prior to when systems are built. How might I work in solar PV3? There are, on the larger projects, always lawyers needed to set up the agreements for the power purchase agreements, which we'll talk about later. This is, instead of buying PV systems outright, you're buying the actual electricity they generate through power purchase agreements. Lawyers are required to set up those agreements, which are rather complex. Accountants are required for this field as well. They establish pro forma agreements. Pro forma is just a fancy term for, is this project feasible going forward? And then they also vet the projects before they're built. Vetting is just making sure that everything lines up and that the project's risks are minimized or mitigated. This final slide I have for you is going to introduce 2 key websites that we're going to use throughout our training. The first one is the National Renewable Energy Laboratory website, found here at NREL. That website contains our PV Watts version 1 analysis, which is a software that's free download on the internet that will tell us exactly what a PV system will produce over a 12-month period based on climatic conditions there. They also have a systems advisory model there called SAM. That is another PV tool that we'll use to make sure that big, actually in small systems too, but larger commercial systems will actually vet out and function the way that we say that they will, with all of the rebates. This one brings in time and use of money and that sort of thing. So this is an important website with 2 tools that I'm introducing here. DSIREUSA.org is a national compilation of statewide renewable portfolio standards. Sounds like a lot there, but it's renewable portfolio standards are a quota system for the public utilities But this site has all of the statewide mandates and all the statewide incentives in the U.S. Now, before I move on, I'm going to just switch briefly to the National Renewable Energy Laboratory. It's got a lot of cool tools. They really are on the cutting edge of technology in regard to renewable energy. I'm going to then show you the other database that I talked about, which is DesireUSA.org. The Desire shows us it's from the U.S. Department of Energy, but also from the North Carolina, you can just make that out, Solar Center. This is a great think tank that shows all of the renewable incentives for each state. For example, if you're coming to us from Maryland, and I click on Maryland, this site's going to bring up a list of incentives for Maryland, especially in the renewables. This is critical to our study of this technology because we're going to be referring to these programs and particularly regulations as we move through our solar PV course. I hope this has been a great introduction to our first class, and I'm looking forward to working with you as we discover how solar PV can literally change our world.